Welcome back to the Deep Dive. This is where we get into the nuts and bolts of the tech that shapes our world, trying to make sense of all that complexity.
Yeah, simplify it down to what really matters.
Exactly. And today, we're tackling something you probably use every single day, maybe without even thinking about the sheer engineering behind it, the news feed.
Ah, the feed. Seems simple, right? You just open your app, scroll a bit.
Deceptively simple.
Totally.
Hey.
But underneath that smooth scrolling is, well, it's honestly one of the biggest systems engineering challenges out there. We're basically going under the hood today.
We are. Our mission, really, is to unpack the blueprint for a newsfeed system, not the secret sauce algorithms deciding what you see.
No, not today anyway. That's a whole other beast.
Right. We're focused on the underlying structure. How do they make sure it's fast, reliable, and can handle, just mountains of data? This is about the architecture for speed and scale.
Okay, so first things first, what is a news feed, technically? If you look at, say, the Facebook help page definition, it's pretty straightforward.
Yeah. What's the official line?
It's the constantly updating list of stories in the middle of your homepage. Simple as that.
And those stories are, well, everything, right?
Pretty much. Status updates, photos, videos, obviously, links people share, activity from apps, and all the likes and comments from people, pages, groups, anyone you follow. It's an aggregation engine, basically.
Okay, so before we start sketching out this system, we need constraints. Every engineering project starts with constraints. What are the ground rules, the blueprint parameters here?
Good point. You have to nail these down first. So, number one, format. It absolutely has to work on mobile apps and on the web.
Which straight away tells you need a solid API, right? An application programming interface.
Definitely. A robust API is non-negotiable. Then, core functionality. Two main things.
Let me guess. Posting stuff and seeing stuff.
Exactly. Users have to be able to publish posts. That's the write action. And they need to see their friends' posts, the read action. Pretty fundamental.
Okay. And how are those posts sorted? Because modern feeds feel complex, algorithmic.
They are. But for this initial design, we're making a key simplification. We're assuming reverse chronological order. Newest stuff at the top.
Time-based, okay. Why that simplification?
Because adding algorithmic ranking, figuring out relevance, adds enormous complexity to the system architecture itself. We'll touch on that later. But for now, time-based keeps the core mechanics clearer and, frankly, faster to design initially.
Got it. What about scale? How many friends are we talking?
We need to support users having up to, say, 5,000 friends.
5,000? Wow. That's potentially a huge audience for every single post someone makes.
It is. That fan-out challenge is central. And related to that, the overall traffic. We're designing for 10 million daily active users, DAU.
10 million people hitting refresh multiple times a day.
All day, every day.
Yeah.
The load is immense.
And it's not just text, is it? Content matters.
Big time. We absolutely have to support media files. Images and videos are crucial.
Which means we're not just dealing with little bits of text data. We have potentially large binary files to store and deliver.
Exactly. Storing and delivering potentially massive files quickly all over the world, that adds another layer of complexity right from the start. All right, so given that scale, 10 million users, 5K friends, media files, the very first major architectural decision you make is separation.
Separation, what do you mean?
You can't realistically handle the process of writing a new post and the process of reading or building a feed within the same pipeline, not efficiently. The loads are too different, too spiky.
Ah, okay, so you split the system.
Precisely. The system is fundamentally divided into two distinct, though obviously connected, operational flows.
And I think that's maybe the first big aha moment for anyone listening. When you hit post, that triggers one set of machinery.
Flow one, yeah.
And when you pull down to refresh your timeline, that's a completely different set.
Completely different. Flow one is feed publishing, the right action. This kicks off the second you hit post or send.
Okay, what happens then?
Well, the data itself, the content, needs to be saved, written to databases, caches. But then, crucially, that new piece of content has to be prepared and essentially pushed out or made available to the news feeds of potentially thousands of your friends or followers.
And on the technical side, the app sends an HTTP POST request?
Yep, something like v1if feed.
Yeah.
And it needs to include the content itself and, of course, an auth token to prove who you are.
So that request hits. What first?
We go through the usual suspects load balancer to distribute traffic, then web servers. These handle the initial connection and maybe some basic checks.
Okay.
Then typically it's a dedicated post service. Its job is persistence, making sure that post content gets safely stored in the main database.
But that doesn't get it onto friends' feeds yet.
No, That's the job of the next critical piece, and often a real bottleneck, the fan-out service.
Fan out, that sounds like what it does.
It is. It orchestrates the process of getting that new post ID distributed to all the relevant followers' newsfeed caches. It manages the push.
Okay, so the fan out service is where that 5,000 friends limit really starts to bite.
Exactly. And running alongside this, you'd likely have a notification service too, handling things like push notifications to tell friends about the new post. But that's somewhat parallel.
Got it. So that's flow 1, publishing. What about flow 2?
Flow 2 is newsfeed building, the read action. This happens every single time you open the app to your home screen or pull down to refresh.
And the goal here is just speed, right? Blinding speed.
Absolutely. The system has to very quickly gather the latest posts from maybe thousands of sources, your friends. And because we decided on reverse chronological sorting for now.
It relies on pre-calculated data.
Heavily. It's mostly about retrieving a list that's already been prepared.
And the API call for this?
Simpler. Usually an HTTP GET request like V1 may feed. Again, you need your auth token.
Components. Still load balancer, web servers.
Yes, but instead of the post service and fan-out service, the request gets routed to the newsfeed service. Think of it as the orchestrator for the read path.
And where does the newsfeed service get the data? Does it query the main post database?
Ideally, no. That would be too slow. It goes straight to the newsfeed cache. This cache holds those pre-calculated lists of post IDs for each user's feed.
Ah, okay. So the fan-out service writes to this newsfeed cache during publishing.
Right.
And the newsfeed service reads from it during feed building.
You got it. Two separate flows, optimized for their specific tasks, writing distribution versus reading aggregation.
Okay, let's zone in on that right side flow 1 for a bit. That POST request comes in, hits the load balancer, then the web servers. Now, we often think of web servers as just simple traffic cops.
Yeah, just passing requests along.
But they actually have a couple of really crucial jobs here, right? Before anything even gets near the fan-out service, security and stability stuff.
Absolutely essential jobs. First up, authentication.
Checking that auth token.
Exactly.
Yeah.
Is this token valid? Does it belong to a real user? Are they actually allowed to post? If that check fails, the request stops right there. Protects the entire system downstream.
Makes sense. And the second job, you mentioned stability.
Rate limiting. This is non-negotiable at the kind of scale we're talking about.
Limiting how often someone can post.
Precisely. Maybe you can only post, say, 3 times per minute or 10 times per hour. Something reasonable.
Why is that so critical?
2 main reasons. One is obvious. Spam. Preventing users or bots from flooding the system with junk posts.
Okay.
But maybe even more importantly, it prevents denial of service or DOS attacks. Imagine a malicious actor, or even just a buggy version of your own app, sending hundreds of post requests per second. Without rate limiting at the edge, that flood could overwhelm your internal services, the post service, the fan-out service, the databases.
It could bring everything crashing down.
It absolutely could. So rate limiting acts as a crucial circuit breaker right at the entrance.
Okay, so the post gets authenticated, it passes the rate limit, now the real heavy lifting starts. Because we hit that fan-out dilemma you mentioned.
Yep. This is the core engineering challenge on the right side. How do you efficiently deliver this one new post to potentially thousands or even tens of thousands of followers?
And you said there are 2 main ways to think about it, 2 models.
2 primary models, yeah. And honestly, both have pretty significant drawbacks when you push them to the limit.
Let's hear about Model A first. You called it fan-out on right, the push model.
Right. Think of this as the proactive or aggressive approach. The moment you hit post, the system immediately calculates who needs to see it, and it pushes that post ID directly into the newsfeed cache for every single one of your followers.
Okay, the big advantage there sounds like speed for the person reading their feed later.
Exactly. It makes the read side super fast. When your friend opens their app, the list of posts, including your new one, is already sitting there in their cache, ready to go. Updates feel real-time, instantaneous retrieval.
But I sense a but.
Oh, there's a big but. Several, actually. The most famous problem is the hotkey problem, or sometimes called the celebrity problem. Imagine a huge celebrity, someone with, say, 10 million followers. They post one photo.
Okay.
With the pure fan-out on right model, that single rate action instantly triggers 10 million cache update operations. The system needs to find that celebrity's follower list, maybe from a database or another cache, and that list becomes a hotkey. It gets hammered with read requests all at once.
Potentially overloading that specific database, shard, or cache server.
Precisely. It creates this massive, instantaneous load spike focused on one piece of data, threatening to slow down or even crash that part of the system. It's a huge bottleneck risk.
Okay, that's a big one. Any other cons to the push model?
Yeah, there's also the issue of wasted resources. Think about your 5,000 friends again. How many of them log in frequently?
Maybe a fraction. Some might not have logged in for months.
Exactly. But with fan out on write, we diligently push your new post ID to the caches of all 5,000 friends, regardless of whether they're active or not,
So you're spending CPU cycles, network bandwidth, cache memory.
serving users who might never even see that update because they don't log in. It's computationally wasteful, especially across millions of users.
Okay, so push is fast for readers, but risky and wasteful. What's the alternative? Model B, fan out on read, the pull model.
This is the opposite approach. It's lazy or on demand. When you post, the system basically does almost nothing in terms of distribution.
Nothing.
Well, it saves the post, obviously, but it doesn't push it out to anyone's feed cache. Instead, when one of your friends opens their app to read their feed,
Then the system pulls your latest posts.
exactly, at read time, the newsfeed service has to go and fetch the latest posts from all the people that user follows, maybe hundreds or thousands of friends, merge all those posts together, sort them by time, and then display the feed.
Okay, I can see the pros immediately. No more hockey problem, right? The celebrity posts, but the load happens later, distributed across all their followers, pulling the data individually when they log in.
Correct. And it's much more efficient for inactive users. You don't waste any resources pushing updates they'll never see.
But the downside seems pretty obvious, too.
It's the killer con. Latency. Speed.
Generating that feed on the fly sounds slow.
It is. Imagine trying to query the timelines of 5,000 friends, get their recent posts, merge, sort, all within the couple hundred milliseconds a user expects a feed refresh to take.
Yeah, that's not going to fly. People would hate it.
It's generally considered too slow for the primary user experience. You'd be staring at a loading spinner all the time.
So Model A, push, is fast but dangerous and wasteful. Model B, pull, is safer and efficient, but way too slow. It feels like we're stuck.
This is where the engineering trade-offs get interesting. You rarely get a perfect solution. The standard practical approach is a hybrid model.
Combining them, how does that work without just getting the worst of both?
You apply them strategically based on who the user is. For the vast majority of users, let's say, anyone with fewer than maybe 10,000 followers.
The normal users.
Right. For them, you use the push model, fan out on write. Because for most users, fast feed loading is the absolute top priority, and the hotkey risk isn't as extreme.
Okay, prioritize speed for the masses.
But for the celebrities, those users who cross that predefined follower threshold, the potential hotkeys,
You switch strategies.
you switch. For them, you use the pull model, fan out on read. When a celebrity posts, their post is stored, but it's not immediately fanned out. Their followers will pull that post individually when they load their own feeds.
So you contain the explosion. You accept a slightly slower feed load for the followers of celebrities in order to protect the entire system from collapsing under the load of those massive fanouts.
Exactly. It's a targeted mitigation. You optimize for the common case, speed via push, and have a specific strategy for the dangerous edge case, safety via pull.
And how does the system know who's a celebrity? Is it just a hard-coded list?
No, it's usually dynamic, based on that follower count threshold. When a user's follower count crosses, say, 10K, the system flags them, and the fan-out service adjusts its behavior for their post automatically.
Clever. Now, you also mentioned something called consistent hashing earlier as a way to help even with the push model's load. How does that fit in?
Right. So even for normal users where we're pushing updates, you still have popular users who might have thousands of followers. Consistent hashing helps distribute the load more evenly across your cache servers or database shards.
How so? What's different from just like basic hashing?
Okay, imagine you have 10 cache servers. With simple modulo hashing, like user %10, all users ending in 3 go to server 3. If server 3 fails, all those users are affected. And if you add an 11th server, now it's user %11, and almost everyone's data needs to move servers, which is a nightmare.
Right, I can see that. Massive reshuffle.
Consistent hashing uses a more clever approach, often visualized as a ring. Both servers and data keys, like userid, are mapped onto this ring. A user's data lives on the server that appears next on the ring after their own position.
Okay.
The magic is, when a server is added or removed, Only the data associated with that specific server or its immediate neighbors needs to be redistributed. Most of the data stays put.
Ah, so it minimizes the disruption and spreads the load more smoothly, especially if one server gets hot.
Exactly. It helps prevent those single-server bottlenecks and makes the cache layer much more resilient and scalable. It's a standard technique in large distributed systems.
Got it. Okay, let's walk through the actual steps the fan-out service takes in that push model for a regular user's post.
Sure. Step 1. Fetch friend IDs. The service gets the post and the author's ID. It needs to know who to push this to.
Where does it get that list of friends or followers?
Typically from a graph database or a specialized cache layer holding that relationship data. Graph databases are really good at quickly answering who is connected to this person.
Okay, so it gets the raw list of, say, 1,000 follower IDs. Step 2.
Filter friends. You don't just blindly push to everyone on the list. The service needs to check rules.
Like what?
It needs to fetch some basic info about those followers, probably from a user cache. Has follower B muted author A? Did author A post this only to a specific close friends list that follower B isn't on? You apply these filters.
Privacy rules, user settings.
Exactly. You generate the final filtered list of recipient IDs.
Step 3. Does it immediately write to their caches?
Not usually directly, no. That would make the initial post request very slow if the fan-out takes time. Instead, it uses a decoupling mechanism, a message queue.
Ah, like Kafka or RabbitMQ?
Precisely. The fan-out service takes the new post ID and that filtered list of recipient IDs and puts them as a message onto the queue.
Why is that so important?
It makes the initial post operation asynchronous. The web server can tell the user, okay, your post is submitted almost instantly because its job is just to get the message onto the queue. The actual fan-out work happens later, picked up by separate workers. It decouples the user's perceived latency from the background processing load.
Right, so the user gets fast feedback. Even if the system is busy, what happens next? Step 4.
Fan-out workers. These are separate processes or services constantly polling that message queue. They pick up a message containing a post ID and a list of recipients.
And they do the cache writing.
Yes. Step 5 is the worker's writing to the newsfeed cache. For each recipient ID in the message, the worker adds the new post ID to that user's feed list in the cache.
Now, you mentioned efficiency here. What exactly gets stored in that newsfeed cache? It's not the whole post, right?
Absolutely not. That would be incredibly inefficient in terms of memory. The cache only stores mappings. It typically pairs like posted user ID.
Just the IDs?
Just the IDs, maybe sometimes with a timestamp.
Huh.
The goal is to keep the cache entries incredibly small.
Mm.
A list of IDs for a user's feed might only take a few kilobytes, whereas storing the full post would take megabytes or more.
And you probably don't store an infinite list either.
No way. You set a limit. Maybe the cache only holds the IDs for the latest 500 or 1,000 posts for each user.
Right.
Because realistically, how far back do people scroll?
Not usually thousands of posts deep.
Right. So you keep the cache size manageable by only storing recent IDs.
Okay, so the fan-out service, using this hybrid push-pull approach in message queues, ensures that the list of relevant post IDs ends up in the newsfeed cache for active users. But it's just a list of IDs.
Just IDs, bare bones.
Which means when I actually open my app to read the feed, there's a whole other process needed to turn those IDs into something I can actually see.
Exactly. That brings us neatly to flow 2, the read action, and the crucial concept of hydration. Perfect transition. We've covered the right side, getting the post ID into the right lists. Now, how do we turn that list back into a usable, viewable feed? That's the read flow, and the core of it is hydration.
Hydration, like adding water to dried food.
Kind of. You're adding the flesh back onto the bones of the IDs.
Yeah.
But first, quickly, where are the actual big media files, the images and videos? We know they aren't stored with the post IDs in the newsfeed cache.
Good question. Where do they live?
They're stored separately, almost always in a content delivery network or CDN.
Like Akamai, Cloudflare, CloudFront.
Exactly. When a user uploads a photo, the post service saves the actual image file to the CDN and just stores the link, the URL, to that image, along with the post metadata in the main post database cache.
Why the extra step?
Speed and efficiency, especially globally. CDNs have servers distributed all over the world. When your friend in Australia views your photo posted from London, their app fetches the image from a nearby CDN server in Australia, not all the way from London. It makes media loading much, much faster.
Okay, so the client app fetches media directly from the CDN using URLs provided in the feed data. Got it. Now, back to hydration. Let's trace the read request.
Okay. You open your app, pull to refresh. Your app sends that CookieD1 Nelly feed request with your auth token,
Hits a load balancer, then a web server.
which routes it to the newsfeed service. This is the orchestrator for reads.
What's its first job?
Step 1 for the newsfeed service, fetch IDs. It goes straight to the newsfeed cache, that cache layer the fanout service wrote to, and retrieves the list of post IDs for your user ID. Let's say it gets back a list of 100 post IDs.
Just the IDs, the bare bones list.
Just the IDs. Now comes the critical step, hydration.
Adding the water or the data.
Exactly. The newsfeed service now needs to get the actual content and context for each of those 100 post IDs. It can't get it all from one place efficiently.
Why not? Isn't there a main post database?
There is, but hitting the main database for 100 different posts, plus user info, plus light counts, that would likely be too slow, involve too many complex lookups or joins. Remember, speed is everything here.
So it uses caches again.
Absolutely. The newsfeed service acts like a conductor. It takes that list of 100 post IDs and fires off parallel requests to multiple specialized caches.
Okay, like which ones?
It'll likely hit the post cache or content cache to get the actual text content timestamp, maybe media URLs for those 100 posts.
Right.
Simultaneously, it needs author information for each post, the username, the profile picture URL. It gets that by querying the user cache, probably using the author IDs associated with the posts.
Okay, user details from the user cache. What else?
Things like engagement counts. It might query a counter's cache to get the latest count and comment count for each of the 100 posts.
So it's fanning out requests within the backend to different caches to gather all the pieces?
Precisely. It's grabbing the post text from here, the author's name from there, the like count from over there, for all 100 posts in the list.
And then it assembles it all.
It stitches it all together. It takes the raw post ID list and hydrates it with the actual data retrieved from these various caches, constructing a complete representation of each post in the feed.
So the output of the hydration step is what? A big structured object?
Usually, yeah. A list of rich objects, often in JSON format. Each object represents a post in your feed and contains everything the app needs to render it. The author's name, profile pic URL, the post text, image video URLs, like counts, maybe info on whether you liked it already.
Okay, so that hydrated list is what finally gets sent back to my phone.
That's the final step, delivery. The newsfeed service sends that fully assembled, hydrated JSON payload back through the web servers over the internet to your client device.
And the app just takes that JSON and renders the feed visually.
You got it. And the entire process, from you pulling to refresh to the hydrated feed appearing, needs to happen ideally in just a few hundred milliseconds.
Which explains why caching is so utterly critical at every stage.
It's the foundation upon which all this speed is built. Without aggressive, multi-layered caching, this whole architecture grinds to a halt.
Okay, let's talk specifically about that foundation then, caching. You've mentioned several different caches already. Newsfeed cache, user cache, post cache, counters cache. Why so many? Why not just have one massive cache for everything? It seems simpler.
It seems simpler, but it's usually less efficient and less resilient. The reason for multiple specialized cache layers boils down to a few things. Different data access patterns, different data sizes, different update frequencies, and failure isolation.
Failure isolation.
Yeah. If your user cache goes down, maybe profile pictures don't load for a bit. Annoying. But if it's separate from the newsfeed cache, users can probably still see the list of posts if everything was in one giant cache and it failed.
The whole feed experience dies.
Exactly. Specialization gives you resilience. Plus, you can optimize each cache layer for its specific job.
Okay, let's quickly recap the 5 key layers you typically see in this kind of system design. Layer 1, the newsfeed cache.
We know this one well now. Stores the lists of post IDs for each user's feed, organized by recipient user ID. Super high priority for speed. It's hit on every single feed load.
Layer 2, the content cache or post cache.
This holds the actual data about each post. The text content, the timestamp metadata, maybe the media URLs, links to the CDN. It's keyed by post ID.
And you mentioned a hot cache within this.
Often, yes. It's a sublayer. If a particular post suddenly goes viral and gets millions of views per hour, you don't want every request hitting the main content cache server for that post. The system detects this hot content and promotes it to a smaller, faster, often more expensive like in-memory, hot cache layer to handle the temporary spike without overwhelming the main cache.
Smart. Okay, layer 3, the social graph cache.
This is crucial for the right path for the fanout service. It caches the relationship data. Who follows whom? Who is friends with whom? What groups does this user belong to? Keyed by user ID. It needs to be super fast for fan-out lookups.
Right, to get that initial list of followers. Layer 4, the action cache. What's this one?
This stores data about your specific interactions with posts. Did you personally like post X? Did you comment on post Y?
Ah, so it's personalized interaction data.
Exactly. When the newsfeed service is hydrating your feed, it queries this cache using your user ID and the post IDs to know whether to show the like button as already pressed or maybe highlight posts you've interacted with.
Got it. And finally, layer 5, the counters cache.
This just stores aggregated numerical counts. Total number of likes on post X, total number of comments on post Y, maybe a user's total follower count, total following count.
Why keep counts separate? Can't you just calculate them?
Calculating them on the fly by querying all likes or comments from a database would be incredibly slow, especially for popular posts. So you maintain these counters separately. When someone likes a post, you increment the counter in this cache asynchronously.
Asynchronously, meaning it might not be instantly perfectly accurate.
Exactly. It's often eventually consistent. The like action updates the main database, sends a message to update the counter cache, but the cache update might take a second or two. But that small delay is usually acceptable for aggregate counts, and it keeps the read path lightning fast because you're just fetching a pre-calculated number.
Wow. Okay, so the newsfeed service during hijaction is really acting as an orchestrator, pulling bits of data from potentially all 5 of these cache layers simultaneously, the list from newsfeed cache, content from content cache, relationships maybe indirectly via user cache, your actions from action cache, and totals from counters cache.
That's a great summary. That specialization and layering is what allows the system to assemble that rich, personalized feed in milliseconds by avoiding slow database hits as much as absolutely possible.
And cache invalidation must be a nightmare if someone deletes a post.
Oh yeah, that's a whole topic in itself. When a post is deleted, you need to trigger operations to remove its ID from all relevant newsfeed caches, invalidate its entry in the content cache, potentially update counters. It has to cascade through the system reasonably quickly.
We've built this incredibly fast, cache-heavy system for reading and writing feeds. But underneath all those cache layers, there's still the persistent storage, the databases.
When we think about scaling this beyond 10 million DAU, maybe to hundreds of millions or billions, what are the big challenges at that database tier?
Yeah, the database layer is where the really hard, expensive scaling problems often live. Caching helps delay the pain, but eventually you hit database limits. The first fundamental choice is how you scale.
Vertical versus horizontal scaling.
Exactly. Vertical scaling means making a single database server bigger and more powerful, more RAM, faster CPUs, faster disks. It's simpler initially, but you quickly hit physical limits and the cost becomes astronomical.
So you have to go horizontal. At this scale, horizontal scaling, also called scaling out, is the only viable long-term path. That means adding more database servers, not just bigger ones, and distributing the data and load across them.
Which leads to the database type question. Traditional SQL or NoSQL?
Most large-scale systems like this end up using a hybrid approach. You might use a SQL database, like PostgreSQL or MySQL, for data that requires strong consistency in complex transactions, maybe user account information, billing, certain relationship mappings.
Because SQL is good at enforcing structure and rules.
Right. But for the sheer volume and velocity of things like posts, comments, likes, log data, where write speed and flexible schemas are key, you often lean towards NoSQL databases, like Cassandra, MongoDB, DynamoDB. They generally scale out more easily for simple write-read patterns.
Okay, hybrid makes sense. What about keeping the database available if the main database server goes down?
Disaster. So you absolutely need replication. The standard model is master-slave replication. All write operations go to the master database server.
Only the master takes writes.
Typically, yes, to maintain consistency easily. The master then replicates those writes to one or more slave servers. These slaves are identical copies.
And they're just for backup.
They can be used just for failover backup, but crucially, you also use them as read replicas. You direct all or most of the read traffic to the slave servers.
Ah, so the many read requests, like fetching post details during hydration if it's not in cache, hit the replicas, taking the load off the single master.
Exactly. It protects the master from being overwhelmed by reads, allowing it to focus on handling writes efficiently.
Now, you mentioned consistency. SQL databases are usually strongly consistent. NoSQL often favors eventual consistency. How does that play out here?
It's a fundamental trade-off. Performance versus immediate accuracy. We touched on this with counters cache. For many parts of a newsfeed system, eventual consistency is acceptable and necessary for performance.
Like count being a second or two behind.
Yeah, or maybe when you post something, it takes a few seconds to appear for all your friends everywhere in the world. That slight delay is often acceptable in exchange for a system that feels fast and responsive overall. You wouldn't accept eventual consistency for, say, your bank balance, but for social media feeds, it's usually fine.
Okay. And if we're scaling horizontally, adding lots of servers, how do we actually divide the data up? You can't just copy everything everywhere.
Right. You need database sharding. Sharding means partitioning your data across multiple database instances, shards.
How do you decide what data goes on which shard?
You need a shard key. For a user-centric system like a newsfeed, the most common shard key is the user ID. All data related to a specific user, their posts, their profile info, maybe their feed list, if stored in the DB, lives on the same physical shard.
Why shard by user ID?
Because the most common access pattern is fetching data for a specific user. By keeping all their data together on one shard, most queries become very efficient. They only need to hit one machine.
Makes sense. But what if you need data that spans multiple users, like finding all posts mentioning a certain hashtag? That data would be scattered across many shards.
And that's the pain point of sharding. Cross-shard joins or queries are notoriously difficult and slow. You actively design the system to avoid them whenever possible,
Ow!
often by denormalizing data, storing copies where needed, or by using separate specialized systems like a dedicated search index, e.g. Elasticsearch, to handle those kinds of cross-cutting queries rather than trying to do them across the sharded primary databases.
Okay, database scaling is clearly a huge topic. Are there other essential practices for keeping the whole system running smoothly at scale?
Definitely. 3 quick ones come to mind. First, keep your web tiers stateless.
Stateless web servers, meaning they don't store any user session info locally.
Correct. All session state should be stored in a shared cache or database. This means any web server can handle any user's request at any time. If one server fails, the load balancer just sends the user to another one seamlessly. It also makes it incredibly easy to scale the web tier up or down just by adding or removing servers.
Critical for handling traffic spikes. Second,
Maximize cache usage. This sounds obvious by now, but it's paramount. Every request served from a cache is a request that didn't hit your more expensive, harder to scale database layer. Cache hit ratios are a key metric to watch.
protect the database at all costs. And third,
Leverage message queues for decoupling. We saw this with the fanout service. Using queues between different components, like post-service fanout workers, allows parts of the system to fail or slow down temporarily without causing a cascading failure. The queue acts as a buffer, improving overall resilience.
makes the system less brittle.
Much less brittle. And underlying all of this, of course, is monitoring. You need constant monitoring of key metrics.
Like what?
Things like QPS, queries per second, on each service, especially during peak hours, helps with capacity planning. Error rates, obviously, but crucially for user experience. Latency. How long does it take to publish a post? How many milliseconds does that feed refresh take? Low latency is the ultimate goal and measure of success for this whole complex machine. Hashtag, outro.
Wow. Okay, that was quite the deep dive. We started with a simple idea, a list of updates, and ended up designing these two incredibly intricate flows for publishing and retrieval.
Yeah, navigating the fan-out dilemma, the 5 layers of caching.
Right. Through to database sharding and eventual consistency. It really highlights just how much engineering goes into making something feel effortless when you use it.
And we saw how that crucial trade-off in the fan-out model, push for most, pull for celebrities, is really driven by the need for speed and system stability.
And that entire architecture, all that complexity we just walked through, was built fundamentally on one simplifying assumption we made at the start.
The reverse chronological sorting, newest first. And that's maybe the final thought to leave people with. Think about how much of this system, the pre-computed lists in the newsfeed cache, the relatively simple hydration, relies on just needing the latest stuff.
What happens if you change that requirement?
Well, think about modern feeds. They're not just reverse chronological anymore, are they? They're ranked by some complex engagement or relevance score.
Right. The algorithm decides what's best for you to see, not just what's newest.
So if your goal shifts from show the latest 100 posts to show the 100 most relevant posts based on hundreds of real-time signals, suddenly that neat separation of concerns and pre-computation gets blown apart.
How so?
The fan-out service can't just push an ID anymore. Maybe it needs to push initial scores. And the newsfeed service can't just fetch a static list of IDs from a cache. It might need to fetch thousands of potential candidates, run intensive ranking models on them in real time considering your recent activity, the post's virality, time decay, all just to pick the top 100 for you right now.
That sounds computationally terrifying. You're not just retrieving data, you're running a personalized machine learning model for every user on every refresh.
It's a fundamentally different and vastly more complex system design problem, moving from simple retrieval to real-time personalized ranking. That's really the next evolution, the next massive challenge these systems constantly grapple with.
Something to definitely think about next time you're mindlessly scrolling. That's all the time we have for today's deep dive. Thanks for joining us.
Yeah, I hope you found it interesting. Keep exploring the engineering behind the technology you use every day.